CUDA. What is CUDA? CUDA stands for Compute Unified Device Architecture, and it's all about utilizing the GPU for general purpose computing and not just for graphics. Parallelizing a program on the CPU gives us diversity in the tasks we can run on each core, but we don't get a lot of cores to work with. Parallelizing a program to run on the GPU doesn't give us much diversity for each core, but it does give us thousands of them. Programs that need to run similar calculations on a lot of different datasets is therefore the perfect fit for GPU computing, which is why we use it for graphics. But there are other applications that also need this kind of processing, especially in the field of research and science. To understand what CUDA is, it is useful to understand how it came to be. For that, we need to have a tiny look at the history of the GPU and its predecessors. Graphics chips started as a fixed function graphics pipeline used to display video. Over the coming years, these became increasingly programmable, resulting in what NVIDIA called the world's first GPU, meaning graphics processing unit, although Sony had coined the term GPU years earlier, but meaning geometry processor unit. The GPU made it big in the gaming industry, but soon computer scientists and other researchers realized the GPU could boost their scientific applications significantly, spawning the GPGPU movement, or general purpose GPU computing, using the GPUs for more general tasks than just graphics. The problem was that GPUs were made for graphics processing, and the languages used to program applications that could run on them, like OpenGL, were also made for this specific purpose. That meant that scientists had to convert their scientific calculations into something that resembled graphics calculations in order to run them on the GPUs. Seeing the potential of the GPU in the scientific community, NVIDIA started modifying the GPU to make it fully programmable for scientific calculations, and in the process added support for high-level languages like C, C++, and Fortran. The result was CUDA, a programmable GPU consisting of newly developed and appropriately named CUDA cores and the CUDA toolkit, allowing programmers to program code that can run directly on said cores. Together, they form the CUDA parallel computing platform. Now, the CUDA platform, being an NVIDIA trademark, only works on certain NVIDIA graphics cards, including every card in the GeForce, Quadra, and Tesla line since the G8X series from 2006. Now, the hardware obviously isn't free, but the CUDA software is, and it's constantly being updated by NVIDIA themselves, being the only vendors of CUDA. The newest version is 11.0 and it was released this year. By using CUDA, you are going NVIDIA all the way, which can cause you some trouble if you want to use hardware from another vendor in the future, as you would have to completely reprogram your application. CUDA is widespread in a magnitude of fields as the CUDA toolkit provides a wide range of specialized libraries and support. CUDA hardware comes as your standard NVIDIA gaming GPU, but also in specialized GPGPU like their Tesla series developed for data centers. This means that CUDA is available for the standard customer using their home PC, but can also deliver massive power from data centers with software support for many research topics, including topics like deep learning, climate, weather, and ocean modeling. The massive software support, as well as unmatched speeds, is what made CUDA the leading GPGPU parallel computing platform on the market. So how does it work? CUDA allows programmers to specify pieces of the program they want to run on the GPU. The rest of the program runs sequentially on the CPU as usual. Functions that run on the GPU are called kernels, and they're specified with the global keyword. To run kernel functions or code on the GPU in general, we need to allocate some shared memory between CPU and the GPU. CUDA makes memory allocation easy as it automatically provides a single memory space for all GPUs and CPUs on your system. To allocate memory, we can use the CUDA malloc managed function, and to free the memory, we use the CUDA free function. Simple as that. To stop the CPU from accessing shared memory while the GPU function is running, we add the CUDA device synchronize function right after the kernel call. The last step is to add a kernel launcher to the function call, called execution configuration. This tells the GPU how many parallel threads to use on the GPU. So, to the program itself. I grabbed this off a Medium article that I found on the internet and modified it a tiny bit to add some comments and to remove some unnecessary code. Now on the top here we've got three functions. We've got the compare results, the GPU matrix multiply, and the CPU matrix multiply. Because this program first runs a CPU matrix multiply in sequence, and then it runs a GPU matrix multiply in parallel, and then compares the two. So the compare results function are used to compare the two matrices that we get and at the end of each multiplication, the GPU answer and the CPU answer. This is just as we did in the pracs. And then we have the CPU matrix multiply, which is also very similar to what we did in the pracs, just with the pointers instead of the specifying arrays explicitly. And then we have this is the kernel function. It's specified by the global keyword, and it's the GPU matrix multiply function. This, as you can see, has the standard matrix multiply code, but it also has this extra bit of code that it uses in the loop calls. So this is kind of hard to explain, but it's very well explained in the comments above. This calculates unique thread ID in the block, because in the GPU, it runs your program in blocks, and the blocks has a set of threads in it. So the threads in each block need to know what thread they are and what part of sort of the block they're running. And then the blocks also need to sort of know each other so they don't run the same part of the matrix. They want to run different parts. So this is what that does. This explains it pretty well. And we end up with assigned cells of different threads does not overlap with each other, and so there's no need for synchronization, which is what we want. It's good. So here I've specified the size of the matrix is 1000 times 1000. Declared the doubles x and y are the ones we're going to multiply, and then GPU answers and CPU answer is the one we get. Here we use the CUDA malloc managed function to allocate memory in the shared memory space, which we do for x, y, CPU answer, and GPU answer. Then we initialize the array. This is just code that was there from before, so it's not random, but it's sort of random enough. Then we have the CPU calculations. So this is the code that runs that. Here's a timer. This is the CPU calculation, and then all of this code is just timer. So this is a for loop that runs the calculation cycles times, which is specified as 10 times, just so we can get an average. And then it does the same for the kernel GPU. It runs it 10 times, and then it has a timer. Now the function call for the GPU matrix multiply has these extra parameters here in the beginning, in between sets of 3 arrows. Dimension 3 just means you need to multiply this, and then this is multiplied with this, multiplied with this. So this first part before the comma is the size of the blocks, this is the amount of blocks that we're going to use, and then this is the amount of threads per block that I want to run it in. And then we have the normal parameters right here. And after the function call, immediately after the kernel call, we have the CUDA device synchronize function, which synchronizes the memory so that the CPU don't go ahead and use some memory while we're running this, because this blocks the memory, and then we sort of free it up with this function. And at the end, we have the compare results and see if that's successful or if it's not. So coding with CUDA is not as hard as you might think it is. It's not as hard as I thought it was, but it takes a bit to sort of wrap your head around in the beginning. But other than that, it's pretty straightforward. You just apply it to your C or C++ code, and it runs on your GPU. Now, obviously, you have to have a NVIDIA GPU above the G8X series, which luckily I have. So I can run this code, and I have some test results to show you just in a second. So the test results. I was testing in Visual Studio, and it was only Visual Studio that was running. It was not a fresh reboot though, so there might have been some background processes still hanging around. I ran it in release mode with 64-bit and with a 1000 times 1000 matrix. This was the run 1. So you can see CPU calculations used about 2 seconds per matrix calculation, and then the GPU used 0.1 and under, which is very good. We have some other runs here. Run 2, similar 2.6 average, and this is 0.09 average. As you can see, we have the success message, so they are the same. And a third time. So we're sort of hanging around the same values here, so not much changing. So that we have a bit of a competitor comparison. Is CUDA any good? Well, CUDA seems to perform better in almost every aspect compared to its main competitor, OpenCL. Apps utilizing CUDA also run faster than they do by utilizing OpenCL. The benefit of OpenCL is that it's open source, and so it's easier for programs to begin utilizing it. OpenCL can also run on almost any GPU supporting GPGPU, while CUDA only runs on NVIDIA CUDA cores. In terms of functionality, they do essentially the same thing. Allow programmers to choose part of their code to run in the GPU. Both languages also support some CPU programming, but that's not the main sort of idea behind it. The OpenCL is open source, which is good, but use CUDA if you can because it's faster. It's important to remember, though, that GPU computing is only useful for a handful of applications that do these type of calculations. So if you just want to parallelize a program, you might want to check if the calculations you do actually fit to be run on a GPU. And that concludes my presentation. Thank you very much.